Your kid's latest 3D print just lifted off the build plate halfway through, wasted 4 hours and $3 in plastic, and now they're ready to quit. The problem probably wasn't the printer settings or the design file. It was the filament. Most beginners don't realize that material choice makes or breaks the project before you even hit print. I'm Rajiv Patel, and I've watched this exact scenario play out in makerspaces and home labs more times than I can count.
You're listening to the STEM Lab podcast. Quick heads up before we get rolling, the research, data, and script you're about to hear are completely human-written and verified by real authors, but the voice delivering it is AI-generated. I want to be upfront about that from the start. If you've been listening for a while now, thank you. It means a lot that you keep coming back. And if you just found us, welcome aboard. We drop new episodes every Monday, Wednesday, and Friday covering 3D printing, robotics, coding, and all kinds of hands-on STEM projects for young learners. Today, we're diving into something that trips up a lot of beginners, filament types, and how to choose the right one without wasting time and materials. Let's get into it.
Selecting the right 3D printer filament for young makers determines whether a project completes successfully or warps into failure. The material you choose impacts print temperature safety thresholds, ventilation requirements, mechanical strength for functional prototypes, and whether kids develop troubleshooting skills or just get frustrated. We're going to examine PLA, ABS, and PETG through the lens of skill progression, lab safety requirements, and alignment with engineering workflows used in actual product development and industrial design careers. Now, let's talk about what these filament types actually are. 3D printer filaments represent thermoplastic polymers engineered to melt at specific temperatures, extrude through a heated nozzle, and solidify into durable three-dimensional objects. Each material exhibits distinct thermal properties, mechanical characteristics, and chemical behavior that dictate print success rates and safety considerations for educational environments. PLA, or polylactic acid, derives from renewable resources like cornstarch or sugarcane. Print temperature ranges from 190 to 220 degrees Celsius, with minimal odor emission and no toxic fume generation. The material biodegrades under industrial composting conditions, but maintains structural integrity in typical home environments for years. ABS, that's acrylonitrile butadiene styrene, represents the same engineering-grade thermoplastic used in automotive dashboards and Lego bricks. Extrusion requires 220 to 250 degree temperatures and produces styrene vapors that necessitate active ventilation. The material delivers superior impact resistance and temperature tolerance compared to PLA. PETG, which stands for polyethylene terephthalate glycol, bridges PLA's ease of use with ABS's mechanical performance. Print temperatures span 220 to 250 degrees with negligible odor and chemical-resistant properties that withstand oils, weak acids, and outdoor UV exposure. The glycol modification prevents brittleness while maintaining the recyclability profile of standard PET bottles. Understanding these filament types enables intentional material selection based on project requirements rather than trial-and-error consumption of supplies. Filament choice directly impacts layer adhesion, dimensional accuracy, and the learning curve young makers navigate. Moving on to how these filaments actually work. All FDM, or fused deposition modeling filaments, follow identical physical principles with material-specific variations. The printer's extruder motor pushes filament through a heated aluminum block containing a thermistor for temperature regulation. The molten polymer exits a brass or hardened steel nozzle at controlled flow rates, depositing 0.1 to 0.4 millimeter layer heights onto a build platform. PLA solidification mechanics rely on rapid cooling. The material transitions from 200 degrees molten state to solid in 2 to 3 seconds, requiring minimal heated bed temperatures, 50 to 60 degrees, or none at all on printers with textured build surfaces. This quick phase change reduces warping but creates brittleness under sustained loads or elevated temperatures above 60 degrees. ABS cooling behavior presents opposite challenges. The polymer contracts 0.8 to 1.0% during solidification, approximately double PLA's contraction rate. This dimensional change generates internal stresses that pull corners upward from the build plate, unless the heated bed maintains 90 to 110 degrees throughout the print. Draft-free environments prevent uneven cooling that causes layer separation. The temperature tolerance extends to 98 degrees continuous exposure, enabling functional parts for automotive or outdoor applications. PETG combines desirable traits from both materials. Contraction rates fall between PLA and ABS at 0.5 to 0.7%, requiring 70 to 80 degree bed temperatures. The material exhibits hygroscopic properties, meaning it absorbs moisture from ambient air that causes extrusion bubbles and stringing. Filament storage in sealed containers with silica gel desiccants becomes mandatory rather than optional. The extrusion process itself teaches systems thinking. Young makers observe cause and effect relationships between nozzle temperature, print speed, layer cooling, and final part quality. A nozzle temperature 10 degrees too low produces under-extruded weak layers. 15 degrees too high creates stringing and dimensional inaccuracy. These variables mirror process control parameters in injection molding and manufacturing engineering, skills that transfer directly to technical careers. Layer adhesion chemistry varies by polymer type. PLA relies on mechanical interlocking as adjacent layers melt into microscopic surface irregularities. ABS achieves superior interlayer bonding through solvent-like welding, where hot material partially dissolves the previous layer. PETG balances these mechanisms with moderate chemical bonding and excellent mechanical grip. These bonding differences explain why PLA parts split along layer lines under impact, while ABS bends before breaking. Here's why filament selection actually matters beyond just getting a print to finish. Material choice determines which engineering principles young makers internalize versus which they never encounter. PLA creates immediate success with 95% plus first print success rates on properly calibrated equipment. This builds confidence, but masks fundamental challenges in thermal management and material science that professional engineers navigate daily.
I observed this firsthand when my daughter completed 20 successful PLA prints before attempting ABS. The ABS print warped within 15 minutes. Her troubleshooting process? Adjusting bed temperature, enclosure draft prevention, first layer calibration, taught more engineering thinking than her previous 20 successes combined. She now understands why automotive engineers specify ABS for impact-resistant components and why design for manufacturing principles require material properties consideration during the CAD phase. Career pathway alignment matters more than most educational marketing suggests. According to 2025 Bureau of Labor Statistics data, mechanical engineering positions specify CAD proficiency and material selection knowledge as baseline requirements. Product designers who understand polymer behavior, thermal expansion coefficients, and post-processing requirements command 18 to 22% salary premiums over those limited to visual design skills. The filament troubleshooting process builds exactly this material properties knowledge base. Cost efficiency scales with skill development. PLA costs $18 to $22 per kilogram, ABS runs $20 to $25, PETG spans $22 to $28. A single failed large print consumes $3 to $5 in material and 6 to 12 hours in machine time. Young makers who understand material-specific requirements reduce failure rates from 40% to under 10%. Converting material investment from consumable waste into finished prototypes. Environmental considerations differ substantially. PLA biodegrades in industrial composting facilities but persists in landfills without proper temperature and microbial conditions. ABS requires petroleum feedstocks and releases VOCs during printing. PETG shares PET's recyclability profile, but most municipal systems lack the sorting infrastructure. Young makers evaluating these trade-offs engage with life cycle analysis and sustainability engineering concepts relevant to every manufacturing discipline. Let's get into the practical lab specs for filament management.
All three materials require distinct storage protocols. PLA can go without sealed storage for short-term use, under 3 months, but you'll want airtight containers in humidity above 60% to prevent brittleness. ABS needs airtight containers to prevent solvent volatilization that causes diameter inconsistencies, with desiccant packs maintaining relative humidity below 20%. PETG is the most hygroscopic of the three. It absorbs measurable moisture in 48 hours of open-air exposure at 50% humidity, so you'll need vacuum-sealed bags or dry boxes with active desiccant. Now for ventilation standards. This is where the chemical emissions profile drives different lab setup requirements. PLA produces minimal ultrafine particles and virtually zero volatile organic compounds. Standard room ventilation suffices for home lab environments. No specialized extraction required for print volumes under 20 hours per week. ABS releases styrene vapors at concentrations of 25 to 200 micrograms per cubic meter, depending on print temperature and enclosed chamber design. OSHA permissible exposure limits stand at 50 parts per million for 8-hour time-weighted averages. Home labs require either enclosure-mounted activated carbon filters with 100+ CFM extraction rates or printer placement within 18 inches of exhaust fans venting outdoors. This represents the primary reason I recommend ABS only for learners aged 14 and up with dedicated makerspaces. PETG emits negligible VOCs, but generates moderate ultrafine particle concentrations. Standard ventilation meets safety requirements. No specialized extraction necessary. Here's the printer compatibility matrix you need to know. PLA offers universal compatibility. It runs on any FDM printer with a 0.4 mm nozzle and basic heated bed. ABS requires an enclosed build chamber or draft shielding. Heated bed is mandatory, and direct drive extruders are preferred for consistent flow. PETG works fine on standard open-frame printers, but you'll want all-metal hot ends to prevent PTFE liner degradation at sustained 245-degree temperatures, and textured build surfaces like PEI sheets prevent permanent adhesion to smooth glass. Material-specific energy consumption affects lab infrastructure. PLA averages 50 watts during printing with 200 to 220 degree nozzle temps and 50 to 60 degree bed temps. ABS averages 120 to 150 watts with 230 to 250 degree nozzle and 95 to 110 degree bed. An enclosed chamber adds another 40 to 60 watts for active heating. PETG averages 80 to 100 watts with 230 to 245 degree nozzle and 70 to 80 degree bed. Standard 15-amp household circuits handle all three materials without dedicated electrical upgrades. Print completion times remain identical across materials for equivalent geometries. The power difference stems from sustained bed and chamber heating requirements. Let's break down the types and variations within each filament category. Standard PLA serves 90% of educational applications. Manufacturers, including Hatchbox, offer dimensional tolerances within plus or minus 0.03 millimeters for consistent extrusion. PLA Plus formulations add impact modifiers that increase toughness by 30 to 40% versus standard PLA while maintaining identical print settings. The material bridges standard PLA's ease with improved mechanical performance for functional prototypes. Silk or metallic PLA variants incorporate mica or metallic powders for aesthetic finishes. These require 0.5 millimeter or larger nozzles to prevent abrasive clogging and teach nozzle selection principles relevant to industrial additive manufacturing. For ABS variations, standard ABS from suppliers like Filament maintains diameter consistency within plus or minus 0.02 millimeters, critical for reliable extrusion flow calculations.
ABS Plus, or ASA, which is acrylonitrile styrene acrylate, substitutes acrylate for butadiene, improving UV resistance and reducing styrene emissions by approximately 40%. ASA enables outdoor applications without degradation, but requires identical printing parameters to standard ABS. PETG formulations include standard PETG that balances clarity, strength, and printability for general mechanical parts. Carbon fiber PETG incorporates 10 to 15% chopped carbon fiber strands that increase stiffness by 200 to 300% and reduce layer line visibility. The abrasive fillers mandate hardened steel nozzles. Brass nozzles wear through in 2 to 3 kilograms of use. This material choice teaches composite material engineering and design trade-offs between cost, performance, and tool wear. High-temperature PETG formulations withstand continuous 90 to 100 degree exposure for automotive or appliance applications. Print temperatures reach 250 to 265 degrees, requiring all metal hot ends with no PTFE components. Progressive skill paths move from PLA to PETG to ABS as young makers demonstrate mastery of printer calibration, environmental control, and safety protocols. This sequence builds troubleshooting capabilities incrementally rather than overwhelming beginners with ABS warping challenges. Let me tackle some frequently asked questions. Which filament types work best for complete beginners? PLA delivers 95% first print success rates on properly calibrated printers with minimal safety supervision requirements, making it the optimal starting material for makers aged 8 to 13 before introducing thermal management challenges and ventilation protocols required for ABS or advanced PETG formulations. Can kids safely print with ABS filament at home? Young makers aged 14 and up can safely print ABS in home labs equipped with either enclosed printers featuring activated carbon filtration or printer placement within 18 inches of exhaust fans venting outdoors to maintain styrene concentrations below OSHA permissible exposure limits of 50 parts per million during sustained print operations. How long does each filament type last in storage? PLA maintains print quality for 12 to 18 months in sealed storage with desiccant, or 3 to 6 months in open air depending on ambient humidity. ABS lasts indefinitely in airtight containers, but degrades in direct sunlight. PETG requires vacuum-sealed storage or dry boxes for shelf life beyond 6 months due to hygroscopic moisture absorption.
What temperature differences matter most between filament types? PLA prints at 190 to 220 degrees with minimal bed heating requirements, enabling use on basic printers. ABS demands 230 to 250 degree nozzle temperatures and mandatory 95 to 110 degree heated beds to prevent warping. PETG occupies the middle range at 230 to 245 degrees with 70 to 80 degree bed temperatures and all metal hot end requirements for sustained use. Which filament builds the strongest functional parts? ABS delivers superior impact resistance and temperature tolerance to 98 degrees for automotive and outdoor applications. PETG offers better chemical resistance to oils and weak acids with comparable tensile strength. PLA provides adequate strength for non-load-bearing prototypes but becomes brittle under sustained mechanical stress or temperatures above 60 degrees. Let me wrap up with a summary. Material selection represents the first engineering decision in every 3D printing workflow. PLA offers immediate success for learners aged 8 to 13, building design confidence and CAD to physical object comprehension. PETG introduces chemical resistance and mechanical performance concepts for makers aged 12 to 16, progressing toward functional prototyping.
ABS teaches advanced thermal management and ventilation engineering for dedicated learners aged 14 and up operating in properly equipped makerspaces. The progression from PLA to PETG to ABS mirrors exactly how product development teams specify materials based on performance requirements, cost constraints, and manufacturing capabilities. Young makers who internalize this decision framework develop the engineering judgment that differentiates system designers from tool operators, the distinction that determines career trajectory in technical fields. Start with PLA. Expand capabilities intentionally as troubleshooting skills develop, and prioritize material property understanding over print volume.
That's it for this episode of the STEM Lab podcast. Thanks for listening. I hope this cleared up some of the confusion around PLA, ABS, and PETG. We've got new episodes dropping every Monday, Wednesday, and Friday. If you found this one helpful, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It's genuinely the best way to help other parents, educators, and young makers discover the show. And make sure you hit subscribe or follow so you get notified the second a new episode goes live. See you next time.